Hello, welcome back. So in today's video, we are going to look into yet another important carbohydrate very similar to the glucose that we saw previously, and this is fructose. And to talk about the physical properties of fructose, we can see that fructose by appearance, it's a white crystalline solid, and taste wise it is very sweet. It's sugar, and this comes under the classification of monosaccharides. And the difference is, this is levorotatory. It rotates plain polarized light towards left. Fructose is levorotatory, while the previously mentioned glucose was dextrorotatory. And the specific rotation of fructose is found to be approximately minus 92 degrees. And if you consider the solubility of fructose, so it is found that fructose is completely soluble in water, whereas it is sparingly soluble in organic solvents like alcohol, and it is completely insoluble in other organic solvents like ether. Okay, now to look into the structure of fructose. So fructose, from elemental analysis and molecular mass determination, it was found that the molecular formula of fructose is exactly same as that of glucose. This is also C6H12O6. And this fructose, for formulating a structure for it, several organic reactions were performed, and based on the products that were obtained, structure was obtained for fructose. So first thing was this on treatment. Fructose on treatment with HI and red phosphorus would give rise to a normal hexene, which confirms that fructose structure has 6 carbon atoms in a long chain. Right? 1, 2, 3, 4, 5 and 6. 6 carbon atoms are there in a long chain, first thing. Secondly, if you treat fructose with hydrogen cyanide, this would give rise to a cyanohydrin. And if you treat this fructose with hydroxylamine, you would get an oxane. So from these two reactions, these two are characteristic reactions of carbonyl compounds. So from these two, you can find that my structure, fructose has either an aldehydic group or a ketonic group. Either of the two functional groups are present in my fructose molecule. And then fructose, if you treat with bromine water, that is, if you try to make fructose undergo a mild oxidation, it doesn't happen. Fructose does not give rise to any acid on treatment with bromine water. So this rules out the possibility of fructose having an aldehydic group. So we can say that fructose is having a ketonic group. From these two, it was either of the two, and from bromine water treatment, it has ruled out the possibility of aldehyde, and finally we have the ketonic group. And then finally, if you try to find out where this ketonic group is actually present on which carbon atom, so for that, if you make fructose to undergo strong oxidation with a stronger oxidizing agent like HNO3, you will get a mixture of acids like glycolic acid and tartaric acid. And the breakage happens at the second position, C2. So the molecule breaks at the second position to form this mixture of acids. So we can confirm that this ketonic group is present at the second carbon atom. And based on all these reactions, we can formulate the structure of fructose to be like 1, 2, 3, 4, 5 and 6. 6 carbon atoms in a long chain, and 1, 2. At the second position, we have this ketonic group, and the rest all are filled with HOH groups. So this top is CH2OH, and this one has OH on the left and H on the right. This one has H on the left, OH on the right, H on the left, OH on the right, and the last one is again CH2OH. Okay. So this is the structure of fructose with a ketonic group at the second position and the remaining being HOH groups with 6 carbon atoms in total. Okay, so from this structure, let's try to draw the products. So structure of the product. So normal hexene, as we all know, it's just a 6 carbon atoms together, and hexane structure, normal hexene. And if you come to cyanohydrin with hexene, this particular molecule, the product that would be formed is like CH2OH. At the second carbon, we have OH and cyanide group, and then these three CHOH groups will be there. I'll just write them together. COH 3 times, and finally we have CH2OH. See, right. This would be the product that is formed if you treat with this fructose with cyanohydrate. At the second position, the ketonic group changed to OH and CN. And if you consider an oxime, how is an oxime formed with hydroxylamine? So what happens is, again the same thing at the ketonic position alone. At this ketonic position, what happens is it becomes C double bond N OH. With NH2OH, H2O would go out and we get C double bond N OH. So this would be the oxime that is formed. With bromine water, no reaction is being formed. And with HNO3, how is it? It happens. A breakage happens here at this position. So one thing that you get is CH2OH with COOH. This top portion goes as CH2OH, COH, and that is glycolic acid. And what happens to the bottom portion? That comes out as tartaric acid, and that is COOH. Then the remaining two carbons is CHOH. CHOH 2 times, and the last group also, CH2OH, also comes out as COOH. This is tartaric acid, top and bottom acidic groups, and at the middle you have CHOH 2 times. So this is tartaric acid and this is glycolic acid. And one thing when I told about the structure, one reaction that is not mentioned here is the OH groups. How did we find out that? These are all hydroxyl groups. That is similar to glucose. It was discussed in glucose, that is treatment with acetic anhydride giving pentacetate. So here also fructose also treatment with acetic anhydride would give rise to pentacetate. It's not mentioned here. But from that pentacetate, you can find that these are all OH groups. 5 OH groups are present. 1, 2, 3, 4, 5. So when you treat with acetic anhydride, it is all these OH groups that gets converted to acetates, OAC, right? So from that they found out the structure has 5 OH groups also. That's not mentioned here. Apart from that, these are the reactions and these are the products that are obtained from this structure. Okay. The structure of fructose that we saw was the open chain structure. It's an open chain. But similar to glucose, fructose also has 2 stereoisomeric forms, alpha and beta forms, and when you allow them to stand for some time in a dissolved state, they change from one form to another. Their specific rotation starts changing spontaneously. This we already learned in case of glucose to be called as mutarotation, and that same property of mutarotation happens in case of fructose also, where it has 2 anomeric forms, alpha fructose and beta fructose. So from that mutarotation property, we can actually find out that fructose, instead of being an open chain structure, this also shows a closed ring structure. So one possibility, a ring structure, it will form by having a ketonic group, an ether group, O linkage would come in. So how does that happen? So one possibility is the linkage will happen here. At the second carbon, this ketonic group, that is where the linkage will come. This ketonic group will come and link with this OH group, CH2OH. This is the linkage. This is where the linking of an oxygen atom comes. And that is how we get the cyclic structure of fructose. So let's draw the cyclic structure. So one possibility is C, and then this carbon I'm drawing, the second carbon. It has this ketonic group would become OH, and this top portion would come here as CH2OH, and then remaining things remain the same, OH and H. Then it's this carbon which remains as H and OH. Then we have this carbon, 5th carbon, that remains again as H and OH, and finally the CH2OH that would come out as CH2, and instead of this OH, actually this is where the linkage would happen. And oxygen group. Like an ether formation, a linkage is formed. A closed lactone is being formed here. This is our alpha form of fructose. This is alpha fructose. Okay. Similarly, if you consider the beta form, the difference is in this carbon. Here is the difference. In case of beta, this CH2OH, same structure with CH2OH going to the right and this OH coming on the left. Again, everything else remains the same. That is, we will have the structure as this carbon atom. OH comes here on the left and CH2 comes on the right. Okay, the CH2 goes here and this ketonic groups OH comes on the other side. Then we have the next carbon. Everything else remains the same. OH here, H here. Then C, HOH, C, HOH, and finally we have the CH2 groups. And instead of this OH, it is that new oxygen linkage. From the topmost carbon to the bottommost carbon, we have this ether linkage, lactone. So this is the beta form. Okay. So here we have the alpha form, here we have the beta form, which differs only at the first position, where it is either CH2 on the left or CH2 on the right. And this is the closed cyclic ring structure or fructose. Okay. These alpha and beta form can also be represented. These cyclic structures can be represented in yet another form, which is the Haworth structure. Okay. So Haworth structure means, first thing is, we look into this, how many 1, 2, 3, 4, 5 carbon plus 1 oxygen, totally 6. So a ring of 6 atoms, that is 5 carbon atoms and 1 oxygen atom, total of 6 atoms would form a ring together, would form like a hexagonal shape ring, like similar to that benzene shape and all. So this would be the ring structure, and now starting from here, this is 1, 2, 3, 4, 5. So it's like, that's how this also goes. This is my first carbon, this is my second carbon, this is my third carbon, this is the fourth, and this is the fifth one, and oxygen being the sixth. 1, 2, 3, 4, 5. Right. So now let's substitute these. And how do we substitute? Like we saw previously for glucose, everything that's on the left would be represented on the top, and all the substitutions that are on the right of the carbon atom would be substituted at the bottom. So for this first carbon, we have CH2 here. CH2OH, right? On the left, OH on the right, so it comes at the bottom. Then for the second carbon, OH on the left, so OH comes top, H on the right, so that comes at the bottom. For the next third carbon, H is on the left, so that's on the top. OH is on the right, so that's at the bottom. For the fourth carbon, H is on the top, and OH on the right comes at the bottom. And for the last fifth one, it is both H and H. It's a CH2, so H and H. So its position doesn't matter. It's H and H. So this is the Haworth projection, and this ring structure, that ring we have, no 6-membered ring, that is called pyranose. That ring is pyranose, and this can be, this is alpha form, so this is alpha D fructopyranose. Right. This is the fructopyranose. Like we had the glucopyranose structure, this is the fructopyranose structure. Similarly, for the beta form also, you can go for a pyranose ring structure, which is, we have again a 6-membered, 5 carbon atoms plus 1 oxygen. Right. And all these are the different possible carbon groups. right? So where we can have the substitutions. So all those on the left would be at the top, all those on the right would be at the bottom. So the only change compared to alpha form is that on the first carbon atom, CH2 will come at the bottom, OH will come at the top. So this is the only change. So first carbon atom, now OH is on the left, so OH comes here, CH2OH comes at the bottom. Similarly, we have for second carbon atom, OH here, H here. Third carbon atom, H here, OH at the bottom. Fourth also, H on the top, OH on the right. And for the fifth one, it is CH2, which means both are hydrogen, so we just have to put H in H. And this form is the beta D fructopyranose. Okay, so we have the two pyranose forms, Haworth projection. It is the cyclic structures alpha D fructopyranose and beta D fructopyranose. That pyranose structure of fructose happens when fructose exists in the free form. But fructose also can sometimes exist in a combined form with other carbohydrates like glucose. Like in the case of sucrose, where it's a combination, if you hydrolyze glucose, sucrose, you will find that it's a combination of glucose and fructose. So fructose is existing with glucose. So in such cases, this fructose shows yet another Haworth form, which is the furanose form. That is, it has 5 atoms. It's a 5-membered ring, furanose form. And there, instead of this linkage, O linkage being here at this 5th carbon, it will shift. This is not where the linkage takes place, and the linkage where it happens is here. It will be CH2OH, and it is here. The linkage happens here. This will be the alpha form. Everything else remains the same, except that instead of that linkage coming to the bottommost carbon, it happens at the 4th carbon. Okay, the oxygen linkage. So this is how it exists. Similarly, in the beta form also, instead of the linkage being there, it is just that linkage will be here, and this will stay as CH2OH. Okay, everything else is the same. So now it becomes a 5-membered ring, right? Now let's draw the 5-membered furanose form of fructose, alpha form. So we have the oxygen and we have the 5-membered ring with 1, 2, 3, 4. All these places we can have the different possible substitutions, and everything on the left would come at the top and everything on the right would come at the bottom, right? So for this one, we start on here, CH2OH and OH at the bottom. Then here for the second one, OH is at the top, H is at the bottom. For the next one, H is at the top, OH is at the bottom. And for the last one, we saw previously for glucose also, when you have something like one pointing this side, one pointing downwards, we can rotate it and you can actually find that it is the CH2OH for this particular 4th carbon atom. It is the CH2OH which is on the left and H is on the right. Okay, so we put the CH2OH and this H would be at the bottom. So this is the alpha D fructofuranose. This is the furanose structure. Okay, and if you consider the beta form of that, what can we see? Here also we will have the same 5-membered ring. Oxygen at the center, 1, 2, 3, 4, 5. With the substitutions coming on each carbon atom. Okay, now if you look at the substitutions, for the first one, OH is on the left and CH2OH is on the right. Remaining, everything remains the same as that of alpha D fructose. So this is OH, H, then it is H, OH. This similar to this one. You turn it, you can see that it is actually the CH2OH group is on the left and the H is on the right, and this structure is the beta D fructo furanose. This is the furanose form. Okay. Previously one was the pyranose form. We had a cyclic structure. We had Haworth projection, and in two forms, pyranose form and furanose form. Okay. So that's it for fructose. I hope you understood this concept. Thank you. Have a nice day.